Let's take a look at another example of centripetal force and vertical circles. A physics student riding a roller coaster decides to sit on a scale as she goes through the track so she can examine the relationship between her speed and the reading on the scale. When the ride begins at position A, over here, she's at rest and the scale reads 600 newtons. Draw free body diagrams for the student at points A, B, C, and D, then calculate the values in the table. So first of all, the reading on the scale is normal force. It's going to be the upward force. Actually, it could be up or down, but the force of the track pushing on the student. And if this girl is at rest, then the normal force is equal to her weight. But we're going to see as she goes through this roller coaster that depending on how she's moving, her normal force might be greater or less than the force of gravity on her. So she might experience feeling heavier or lighter than she actually is. I'll just make one other note. In this case, we're going to assume the scale is reading 600 newtons. We're going to assume that her mass is equal to 60 kilograms, which means that I'm using a little shortcut, which is that I'm rounding the acceleration due to gravity from 9.8 to 10, okay? So we're just going to assume that the mass is 60 kilograms. All right, so over here at location A, the student is at rest at the top of the roller coaster, and so she's got two forces acting on her. First of all, gravity pulling her down, which we know is 600 newtons. And then the normal force from the track supporting her. That will also be 600 newtons because she's at rest, right? She's vertically balanced. All right, as she moves to location B, she now finds herself at the bottom of this big dip. And gravity is still going to pull her down with the same 600 Newton force. But now she will experience a different normal force because she is accelerating. And why is she accelerating? Because this is part of a big circle. Can you see this circular path right here? And when you are traveling in a circle, you are accelerating towards the center of that circle. So the center of the circle would be here, which means that the girl is actually accelerating this way, upwards. We call that centripetal acceleration. And that centripetal acceleration is accompanied by a centripetal, I should say it's due to a centripetal force. So since the centripetal force is upward, we can comfortably say that the normal force is actually going to be greater than the force of gravity. And we'll find out what that normal force is in a second. All right, location C now. The girl finds herself in a new circle here, where the center of that circle is now below her. So now the centripetal force would be downwards, and so she will again have gravity of 600 newtons, but now the normal force is going to be different than before. We don't know what it is, but we can comfortably say that since the centripetal force is down and the girl is accelerating downwards, that actually gravity will be the greater force in this case. We'll go back and actually calculate the difference between those two forces in a moment. And then finally, at location D, now she's in this very tight loop. We can see the circle with an 11-meter radius. And as before, the force of gravity is down 600, not 60. And she, though, is upside down. The track is above her, right? So now the normal force is down, not up. Okay, we don't know what it is. We'll find out what it is in a second. Okay, so let's jump into this. Okay, I'm going to add off to the side of each of these the direction of the centripetal force, okay? At location A, there is no centripetal force because she's at rest. She's not moving in a circle. At location B, the centripetal force is upwards because that's the direction of the center of the loop. And I'm going to label it as the sum of the forces in the centripetal direction, meaning the inward direction. At location C, now centripetal is down because the center of that circle is here below her. And then at location D, the centripetal force is also down. So the sum of the forces in the centripetal direction will be here. Again, because the center of the circle is here and she's up here.